Good afternoon. Thanks everyone. Thanks for the introduction, and also for the mention, Zeger, and for the CubeSat precursor update. So I'm here to tell you a little bit more about the ADCS specific things that have happened on the precursors, which I find very interesting, and I hope you do as well. So just a bit of background. I'm not going to talk about the CubeSat main mission too much because I'm sure you're well aware of what's going on and all the requirements that comes with the mission. Just a brief refresher in terms of attitude control. The CubeSat satellites need attitude control because we want to be able to point the sensors in specific orientation, and we also want to minimize the influence of drag, so that because of the low orbits that the satellites are going into, we don't have a reduced lifetime because of unfavorable orientation. Now the CubeSat project receives money, funding for the various parts of the project, and one of the work packages in the project is also the development of an ADCS module specifically made to cope with the CubeSat scenario. And SSC, under my supervision, has been responsible for that, and we've also worked together with Stellenbosch University, the ESL, to provide a design of a module, and then also 15 flight units of these ADCS modules that will be used throughout the project. And getting back to the precursor mission specifically then, 2 of these flight units have been integrated into the precursor satellites that you just saw Zeger present. And the idea, as Zeger also mentioned then, is to de-risk some of the critical technologies by flying them on the precursor satellites and making sure that they work and that they deliver the performance that we expect from them. I'm just, again, as part of the background, going to talk briefly about the design of the satellites, just so that you know, design of the ADCS, just so that you know what we're talking about. But the real bit that I want to get to is the lessons learned on the flight results. The ADCS module makes use of a suite of sensors and a bunch of actuators. So we've got a 3-axis magnetic sensor that measures the orientation and the size of the Earth magnetic field. And we place that on a boom, a deployable boom. So the idea is that once the boom is deployed, you get less interference from the spacecraft bus electronics and a cleaner magnetometer measurement. We also have photodiodes, not really a necessity for attitude control, but just helps in giving us a bit of extra info. Ideally, we would have 6, 1 on each facet of the satellite, but because of the science unit, we cannot have one in the +X direction, the facet that the science unit is fitted on. But with 5, we can still estimate the sun vector by making some assumptions. We also have a fine sun sensor and a nadir sensor. They make use of optical CMOS cameras and wide field of view optics. And for actuators, we have conventional 3-axis magnetorquers. For the Y and the Z axes, we use rods with a Supra 50 core. For the X axis, we don't use a rod because that would be difficult to accommodate inside the bus. So rather, we have a flat coil that we can fit, that we can easily accommodate between PCBs on the CubeSat bus. And then we also have a single wheel aligned with the satellite y-axis or the pitch axis that operates as a momentum wheel, but it also gives pitch, the ability to control the pitch angle of the satellite. For processing, we have the Cube computer, a generic CubeSat OVC, but we use it for the attitude control processing specifically. One of the nice features on there is the EDAC protected SRAM, which unfortunately on the precursors we haven't been able to use yet. So unfortunately we don't have results of how well the EDAC works, but the idea is to get a bit more reliability by protecting against single event upsets, bit flips, and so on. And just if you integrate all of that into a stack, it looks like that, and it's really as compact as we can make it With CubeSats, I guess that's the important thing. And then the components not shown in that picture are obviously the photodiodes and the magnetometer that have to be mounted externally. Just two videos of what the ADCS is supposed to do. We have two distinct control modes. The one is the detumbling control mode, where the outcome should be a Y-Thomson spin that uses only the magnetorquers. Just get this to play. And we don't require full attitude knowledge at this point. We only need, for the detumbling control mode, we only need an idea of what the Y angular rate of the satellite is. And we can get that either from estimation or from a MEMS gyro directly. So with this control mode active, the steady state situation that you expect is this. Satellite tumbling only about its Y-axis, and that Y-axis also aligned with the orbit Y-axis. And then the following control mode is then the transition into a stable attitude. In this mode we spin up the wheel, and the momentum that we give the wheel, the momentum command that we give the wheel is supposed to match up with the angular momentum of the satellite. So the wheel absorbs the satellite motion and the satellite just goes into a stable orientation. And we still use the magnetorquers there to damp mutations in the other axes. For this mode we need full state attitude information, so both the angular rates and the pitch angle as well. And we've got a full state extended Kalman filter to provide us that makes use of all the sensors that we have on the satellite. So that's the background. Onto the interesting bit. So as Edgar mentioned, initially the satellites came out of the quad pack, and they've managed to receive the beacons, found out that the health of the satellites were fine, and then we started activating the ADCS to see what was going on tumble-wise. The conclusion there was that P1 was spinning at a rate of minus 30 degrees per second about the y-axis, and P2 with plus 30 degrees per second about the y-axis. The fact that the satellite was spinning predominantly about the y-axis was comforting for us, because that's intentional. You'll see in this faded out picture, we intentionally added some dummy masses to the side of the satellite to make sure that the moment of inertia about the body y-axis is actually larger than the other axes. By doing so, you'll find that the satellite will, due to natural damping, end up with a spin rate about this axis with largest moment of inertia. So the fact that both satellites were spinning predominantly about the y-axis tells us that this dummy mass approach actually worked. And that's also an important lesson learned. It is mentioned in the ICD for the ADCS that this is a requirement for Y-Thomson to work. But I'm not sure how many teams are actually considering that, and just hope that it works out that way. But it's quite an important design consideration. And the other thing is also, both satellites ended up with a 30 degree per second spin rate. And as Ziga mentioned, we've now come to realize that there's a natural spin up that occurs when the ADCS is inactive. So the unfortunate thing is we don't know what the actual tip-off rates were when they came out of the quad pack. But probably they were lower than 30 degrees per second. When it came to assessing what the tumble rates were, in the previous slide I told you what they were, but getting there was not such an easy process as just switching on the ADCS and getting some telemetry. The first issue that we had to deal with was our telemetry scaling. The ADCS was designed for the QB50 specification, which says the system has to cope with maximum rates of 10 degrees per second. And clearly we saw higher rates. So our telemetry was scaled to fit in the range minus to plus 32 degrees per second. Outside of this range, if the actual value is outside of this range, the telemetry that you get on ground is a wrapped version of that. And there's a formula that's fairly easy to calculate what the actual rates are if you know that the telemetry is wrapped. But the problem is we had on P2 this situation where really the interpretation can be either there's a positive Y rate and in some points the telemetry is wrapped and it's flipped over to the negative side, or it's the other way. And initially we didn't know exactly which was true. To complicate it even further, we would have hoped that P1 and P2 had the same initial tumble rate, and that's before we realized the natural spin-up. Both satellites were inserted into the quad pack with the same orientation, so we expected them to have the same tip-off rates initially. That's why initially we would rather have corrected P2 to have the same sign, P2 spin rate to have the same sign as P1. The other difficulty that we had was once we've assumed that we activated the V dot control or the detumbling control, and then realized that we have an issue because if the satellite was actually spinning, or if the telemetry had actually wrapped and the V dot controller was doing what it's supposed to be doing, the rates will look like they're increasing. But all we see is the rates going in one direction, but that still doesn't tell us whether they're going in the right direction or not, and maybe we have a reverse torque of polarity. So the issue was solved in the end by requesting real-time magnetometer telemetry at something as close as 1 Hz as we can. And from that, that's the graph that you see at the bottom left there. From that we can deduce that it really is a positive Y spin, and we've also fed that data into the rate Kalman filter on ground to get a manual estimate of what the magnitude of the rates are. The other issue that we have with our detumbling control is that it's not operating as efficiently as we would like. So without going into too much detail about that flowchart, there's two parts to the detumbling algorithm. There's a V dot controller and a Y spin controller. But there's a check just before the Y spin control that evaluates whether the angular rates are low enough for the Y spin to engage. We found later that that check isn't really necessary for stability. The satellite or the detumbling controller is quite stable without that check. But the check is in there in the code, and it's unfortunate because even though we have a dominant spin about the y-axis, the x and the z are never low enough for the y-spin control to kick in. And the v dot control only really damps the x and the z. As a side effect of the products of inertia that we have, it damps the y rate slowly. So the end result is that the detumbling controller is slightly ineffective at damping the rates. Doesn't say it's not working, it's just not it's not like it's going to go to a stable Y-Thomson spin in 10 minutes time. And then another issue that we've come to realize later on is that we have an apparent torque polarity reversal. Again, without going into too much detail, we found that because of the latency between when the magnetometer is sampled and the time that the torque is applied through the torque rods, the polarity of the Y torque seems to reverse at around 30 to 35 degrees per second. So that means if the satellite is tumbling at 35 degrees per second and you activate the V dot controller, the satellite will actually spin up. And to get it to spin down again, you have to reverse the polarity of the torque rod. Long story short, we now have a reliable procedure to recover all the way from plus and minus 85 degrees per second. How we got there in the first place is another story. But from 85 degrees per second, we can detumble using a reverse polarity for the Y torque rod with only the V dot control active. And that brings the rate to about 32 degrees per second, where it kind of levels off, as you can see in this plot. And at that point, the rates are too high to go back to the normal polarity. The satellite will still spin up. So we temporarily do a cross polarity setting where we apply the V dot control output to the X coil. And that brings the rate low enough so that we can do normal V dot from there on. And then you can see that very last portion when the X and the Z rates are finally at zero, we quickly go into a Y-Thomson spin after that. I see my time's almost up, so I'll quickly go through the rest. Current state, we go in and out of Y-Thomson. Satellite remains kind of stable. The reason why the Y-Thompson state isn't maintained all the time is because, as Ego mentioned, the resets we have on the ABC, initially also the operators would put a timeout to the duration that the ADCS was active, and that means there's maybe a few hours that the ADCS is switched off before the next ground station passes and they can command it on again. But normally you would expect the attitude rates to drift if that happens. But what we've seen is over the 48 hours we can get all the way from 2.2 degrees per second back to 30 degrees per second again. This natural spin-up is still kind of speculative exactly where it comes from. We suspect probably solar panel currents acting as talkers. But really to get into such a state you need something that switches on and off at regular intervals. The magnetometer boom deployment, we've confirmed successful boom deployment on P2. Initially we had issues verifying the boom deployment because the satellite was spinning at too high a rate and our telemetry was sampled too low to see from real-time data whether the magnetometer did deploy. But we could still do all of the detumbling regardless of what the stowed or deployed state is. It's only once the Y-spin control activates that it matters whether you're using the stowed or the deployed calibration. And that's also the one test then that we know that the magnetometer on P2 did deploy, is because it was able to do effective Y-spin using the deployed configuration setting. And then also we've used the photodiodes to correlate with the magnetometer measurements, the raw magnetometer measurements, to know that on P2 the boom did in fact deploy. And the same process we can also say that on P1 it did not unfortunately deploy. We've also spun up the momentum wheel. Just a simple test, have the satellite at low rates, ideally at Y-Thompson, and just give the satellite a momentum reference, the wheel a momentum reference. And then we just verify from the angular rates that the satellite is outputting that there's a jump corresponding to what the wheel angular momentum is. And that you can very nicely see in that graph where the jump in angular rate is exactly the 2.2 degrees that we wanted. We've also switched on the fine sun sensor, got some measurements and correlated that with the photodiodes. And then just one last slide about the future plans. For the QB50 main flight, I'm not going to say much. I'm here for the QB50 workshop as well, and I'll give a talk there as well, so we can discuss that further there. But on the precursor flight, what's next is to commission the full Y momentum mode as well. For that, we need to calibrate the magnetometer with in-flight data. That requires the watt functionality. That's going to be part of the new code upload. Once we've done that, we can commission the full state extended Kalman filter and put the satellite into Y momentum mode and have a stable attitude. And then lastly, just want to return Zager's favor where he thanked us. I kind of want to do the same and say thanks to ISIS and to Zager, for the operators, for all the patience with the ADCS and entertaining all our suggestions and theories. Thanks for making it a success.
Thank you very much. Again, we would have time for one question.
I would like to ask you what is the sampling rate of the multimeter and what is the frequency of the control loop?
Both answers is 1 Hz. So the control loop runs at 1 Hz on the Cube computer, and we sampled the magnetometer at 1 Hz as well. But the telemetry that we get back on ground for QB50 precursor is only every 10 seconds. But we have ways of requesting the data more frequently. It's just for the nice periodic signal we get out every 10 seconds.
Okay, thank you.
Thank you very much.